So the goal now is to define the concept of an algorithm. So what is an algorithm? Well, the first analogy that's always given is that it's a recipe. Well, this recipe better be given for a specific purpose. And indeed, you always want to achieve a goal or perform a task if you are giving an algorithm. Okay, but that's essentially an informal algorithm. An algorithm where you're not completely specifying certain things. So an algorithm becomes formal if you're making some specific assumptions on what? On the atomic operations that are available and on the global constraints on those operations. So basically, you have some operations that are available to you that you can use in your algorithm, operations that can be broken down into smaller pieces, and you're using those to explain what your algorithm does. And there are some constraints that you might be ignoring or you might be taking care of. So there are specific constraints that link all those different atomic operations together. For instance, you are not allowed to execute too many of them at the same time or too many of them in succession. Okay, so an algorithm is always given with some background assumption. And this background assumption helps you ignore some low-level implementation details because this is hidden in the global constraints or in the atomic operations. So let's go further with the analogy of the recipe, and let's look at a cookbook. So what's the goal of a cookbook? Well, provided you can fill in a lot of details, the recipes will describe ways to get from basic raw ingredients to a full-fledged meal. So, for instance, if you have a recipe for a lasagna, you can imagine what that is. But let's look at this recipe more closely, and let's see first. So the recipe might tell you explicitly how to prepare a bechamel sauce. So this might be an atomic operation or not. And if it's not an atomic operation, then it will describe it in more detail how to prepare a bechamel sauce. So the atomic operations then that it would use would be more basic than that, and it would give a full description of how to make the bechamel sauce from those more basic atomic operations. Okay, so another parallel I want to draw with the previous slide is that sometimes, most of the time actually, your cookbook will not tell you to throw away ingredients that are past their due date. Okay, so in other words, the cookbook is ignoring some time aspects, some time limitations. So it's ignoring those. Of course, it would not be very practical, but it's assuming that you have flour or whatever, and this flour will be good forever. Also, cookbooks tend to ignore space limitations, maybe a bit less than the time limitation I was pointing out. So if you have a small kitchen, it might become difficult to do some recipes because you don't have many stoves, you don't have very many kitchen counters or much space there. But cookbooks tend to ignore that aspect. So it's the global assumptions here are fairly low. It's not or fairly high. It depends how you look at it. It's not it's not telling you explicitly how to deal with restrictions in time and restrictions in space. Okay, so now that we more or less know what an algorithm is, it's time to go to the programming language, the concept of programming language. So what is a programming language? Well, it's a formalized language, so it's a language that satisfies some formal rules, some formal grammar, and this language can be used to write source code. So source code is just text written in this formalized grammar. But the main point of a programming language is that this source code can be automatically translated into instructions for the CPU. And this language that is used to write instructions for the CPU is called assembly code. So if you remember, we had our data that was here, and we could act on the data. And if you remember, these actions were described in terms of instructions for the CPU. So these actions are given in assembly code. Now, what is a programming language? Well, a programming language is a language that allows you to write source code, so text in this formalized language, so that this source code can be translated directly into, actions on data, so into assembly code. Okay, so the point is that this translation here is automatic. doesn't require human intervention anymore. So that's what a programming language is. Programming language is here, it's the language that you'll write the source code in. Okay, so what is now the art of programming? That's the next natural question. Well, we know that an algorithm is a recipe to perform a task, and it's given under specific assumptions. Okay, we know that a programming language is a formalized language to write source code with automatic translation into assembly code. Well, programming in a programming language that I'll call PL consists of writing down a recipe for the task we want to perform under the assumption of the operations available in the programming language. Okay, so let me try to make this a bit more precise or a bit more concrete. So we have a certain task here on the left that's maybe a bit informal, so maybe not entirely clearly defined. And the goal is for a computer to help us perform that task. So imagine still we have this data and we have this action on data, and we essentially have here the level of assembly code because we have to give the CPU clear instructions that it can understand. And somewhere in between here, we have programming language PL and some of its source code. So the programming language comes with operations that are allowed in the source code, and all those operations, the programming language or the compiler or interpreter for this programming language, we'll get to this later, they know how to translate this into, well, assembly code or data. And this translation here is automatic. Now, the act of programming comes here. It comes from translating the task, which is a bit informal, into this formalized language, this programming language. So the act of programming consists of translating this task into source code written in that programming language. Now, if you go back, if you look at the task that has to be translated here into source code by a human and then automatically translated into data and actions on the data, well, you see that at some point, this translation that the human has to do is not just a translation of the actions on the data, but also on the data. So this is an important aspect, that this programming task always requires to specify how the data is encoded and what the actions are. So how you act on it. So you don't necessarily need to do it at the level of assembly code, which is, remember, very concrete and talking directly to the CPU. But you can actually use some intermediate, more complex operations at the level of the programming language. But that's what programming is. You're translating your task into concrete representation of the objects you're manipulating and concrete actions on those objects. So, for instance, if you have polynomials that you want to manipulate, you want to compute derivatives of those polynomials and things like this, and say your polynomials have integer coefficients, well, at some point, you have to decide, and it might be left informal, but you have to decide that your polynomials are encoded with a list of integer coefficients, or maybe with a string that explicitly includes the variable. So what I mean is you could decide that your polynomial would be encoded as x squared plus 1, or maybe 1, 0, 1, the list of coefficients, and if it was 2x squared plus 1, you could do this, or you could do this. You have to choose a convention for representing your polynomial. But that's an important step in programming. And once you have decided this data encoding, then you can start programming the operations on whichever convention you have chosen. For instance, taking a derivative. Okay. Now, there are many programming languages, and we're just seeing one of them. But each tries to satisfy a certain need, to fulfill a certain niche. And I just wanted to give a little overview first of the many different programming languages that exist. So we have already seen one. So that programming language is assembly code. So it's CPU instructions, essentially. So it's direct CPU instructions talking to either the control unit in the CPU or the arithmetic unit in the CPU. But we've seen that. And then progressively, if you go up here, the abstraction goes up, or at least the complexity of the structures and the operations. Of operations on the data, and of data structures. So the two go hand in hand. The complexity of those operations and data structures goes up, which allows the abstraction level to go up. Okay, so we're starting with assembly code, which is really the most basic language, and we're going up all the way. Or we can go many different ways, but in the context of a course for mathematicians, maybe we will go to computer algebra systems. Okay, so you have a certain task you want to perform. It's the same picture again. A certain task, maybe in the math domain or in some other domain. And eventually you want to go all the way to assembly code. And you have many ways to do this. And actually, before I start, there's one assembly code for one CPU type, but there will be another assembly code for another CPU type, etc. So it really depends on the different on the machine and the underlying machine that you have at the end. So now PCs tend to converge to Intel processors, but not so long ago that wasn't true. A Mac would have a different type of processor, a different type of assembly code that it would be using, and but still now phones, there are different types of phones that have different assembly codes that they understand. So this is still relevant. There are many different assembly codes. But to mitigate this, to help deal with the fact that there are many different assembly codes, people have invented what's called virtual machines. And again, there are many virtual machines that exist. And code that is written for a virtual machine is called bytecode or machine code. And what is a virtual machine? Well, essentially, it's slightly more complex operations than what you can do at the level of assembly code, but it's sort of operations that you expect to be present in every machine, like show a pixel or look at this key press, things like this. And basically, a virtual machine has some basic set of instructions like this that is then translatable automatically into many different types of assembly code. So I'll give you an example of a virtual machine. There is a virtual machine that's associated to Android, the operating system for phones. So Android itself is not the virtual machine, but there is one that is linked to Android. And once you have programmed something for the Android virtual machine, then you can use it for many different types of phones. Same thing with different apps, for instance, for the iPad or something like this. Then if you program for the virtual machine, then you can use it for the iPad, the iPod, and things like that. Okay, so this is a construct that helps us program for all the machines that are here on the right. And then there are other intermediate programming languages like C, C++, JavaScript, and so on. So it depends on the language, but some of them have direct translations to assembly code in different machines, and in particular C and C++. And some others, like JavaScript, go through a virtual machine, which makes them extremely portable and extremely desirable to use for any application that involves the web, where you have to deal with potentially many different types of computers on the user side. Okay, so that's C, C++, JavaScript. And then there is maybe Python, which should be here, but it has a weird status because, especially for Python now, it starts to have many ways of being translated back to assembly code. So we'll see this later. There's certainly things like this. So once it can be automatically translated here, can be automatically translated into many machines, or maybe to JavaScript, it becomes very portable over the web, and you can go all like that. Or it can even directly translate into assembly code, which makes it much faster. All right, and then finally, for a mathematician, maybe, so each time I'm on the right, I make some choices as to what the application domain is, and now I'll make the most drastic choice for a mathematician. There's the computer algebra systems, and the computer algebra systems, well, it might be MATLAB, which helps you solve matrix operations, Maple, symbolic manipulations, Mathematica, general purpose computer algebra system, and then there is also Sage, and So I won't comment very much on those, except to say that MATLAB, Maple, Mathematica have probably a lot of code that is written in C++, but they have their own languages each time, and that you need to learn if you want to start using it. But ultimately, it translates this more abstract code where you can manipulate complex math objects into C++. Now, the last one, Sage, is interesting because Sage is essentially Python. So I'm saying essentially because you can write Python code and this will be Sage code, and vice versa. You can start importing Sage into Python and really program in Python and use Sage just as a library. And this is really a math domain computer algebra system. So you can do a lot of very advanced stuff with all of those. But the interesting bit here is that Sage is directly written in a general purpose language such as Python. So if you learn Python, you're learning Sage essentially. And the advantage is that Python has a lot of documentation on the web, and also it makes it very interlinked. So you can start using Sage from Python, but you can use a lot of other math libraries. So you gain a lot from this interoperability. Okay, so this was for the definition of an algorithm and the definition of programming languages and things.